first of all, we see definition of a set. Actually, we want to learn about group theory, and the basics of group theory starts from set. First of all, we see definition of a set, then move forward to higher topics of group theory and try to understand it. So first of all, we see definition of a set, a well-defined collection of distinct objects. In the definition of a set, here two words are most important: collection, distinct objects, and well-defined. So first of all, we see what is well-defined and what is distinct. In such type of collection which is well-defined and distinct, then this type of collection make a set. Every collection is not a set. So we see definition of a well-defined. Well-defined, it means we decide which element of a set exactly lie or not. Means we have to decide which element exactly lie in it and which element exactly it does not lie in it. For example, we have a set of first 5 numbers, and we clearly tell that 7 and 8 does not belong to that number because we have the collection of first 5 number. So here we clearly define which element exactly lie in it and which not. But if you see, if you collect some collection of intelligent boys, then you have not to decide that which boy include in it and which not, because everyone measures intelligence according to its own scale. That's why it is not a well-defined. So well-defined means we clearly have made a decision about a set and about elements of a set. And distinct elements means different elements having different images. Here we see examples of a set, and then we try to understand about it. Following are the examples. First of all, we see some examples of a set, and to learn about something in more detail, it is necessary to learn the examples which are not satisfy this definition. So that's why we see some examples of collections which are not a set, and some examples of a collection which are set. So first of all, see this definition, and here you see 1, 2, 3, and 6. I collect some first 6 numbers of natural numbers and collect them and write them in a bracket, and we decide it is a set. How we decide it is a set? Which features urge me to say that it is a set? So you see different this collection. In this collection, all elements are different from each other. So this is the first condition of a set, means distinct elements. So all this collection have distinct elements and distincts. Also, we know that which elements exactly lie in it or which element not. For example, you have a set A, and you clearly define, if someone asks you 2 is belong to set A, then you clearly said yes. And if someone asks you 7 is the belong to that set, then you clearly said it, no, it does not belong to A. That's why we clearly decide which element belongs to that set and which element does not belong to set, and this is the definition of well-defined. So these satisfy both conditions of distinct and well-defined, and we, by the definition of a set, distinct and well-defined collection is a set. That's why this collection is a set, and we name this set A. Remember that as we like, we give name to the set, capital letters A, B, C. It is totally depend upon us. This is the name of the set. Or collection of elements. For example, I say I have some collection of elements, and here I do not able to explain which element exactly lie in it or which element not. For example, I say collection, but other does not decide that the collection I have, which element belong to it and which element does not belong to it. So that's why it is not a set. collection of tall boys, we clearly does not tell that which tall boy belongs to it and which tall boy does not belong to it, because everyone measures tallness according to his own measurements or scale. That's why tall boys is not a collection. So collection of sea animals. Every sea animals, I do not decide here which sea animal belong to it and which animal does not belong to it. That's why it is also not a set. So empty set, some one say that question me that this is a set or not. It is very conceptual question, and yes, of course it is a set. It is it has no elements. This is empty set, and empty set is well defined, or well defined because we clearly say that nothing belongs to it. Empty set is a set in which no elements belong to it. That's why it is a well defined, and we clearly decide that which element belong to it and which element not. That's why it is a set, because due to its well defined property. So some important sets which are predefined and used uh, mm, very important in our group theory point of view. Set of natural numbers. Set of natural number, we give the set of natural numbers capital M, and it's start from 1 2 3 and so on. These three dots called ellipses, and it means it continue till at the end. Natural numbers, whole numbers and natural number. Difference between whole and natural number is 1, it is 0. The natural number which includes 0 is then it make whole numbers, and we as whole numbers starts from W, so we name this set W. And set of integers, it is very important set, and very important point of view of group theory. So we see what is a set of integers. The set of integers is starts from all natural numbers and instead or 0, and all negative numbers, -1 -2, and here is the mistake, I think -1 -2 -3 and so on. So these are the set of integers. And set of prime numbers, which are divided by itself or 1. These are the prime numbers, 2 3 5 7 11 and so on. These are the elements which are only have two divisors, which is the number itself and the other number is 1, and it has no other divisor. You see, three divisors of 3 are just 3 and 1, and no other element divisor of 3. That's why 3 is a prime number. Similarly, 5 7 and 11, these are all prime numbers. And next we see set of even numbers. Even numbers are the numbers which is divided by 2, and 2 4 6 8, these are and so on. These are the divisors of so that's why these are the even numbers. And set of odd numbers, which are not divisors of 2, divided by 2. So that's why these are the odd numbers. And you see rational numbers, and rational numbers are the numbers which can be written in the form of P by Q, and P and Q belongs to Z. Here what is Z? Z is the set of integers, and Q does not belong to mean this Q does not be equal to 0. So this is the rational number. So now we see subsets of a set. What is the subset of a set? For example, I explain the subset of a set with the help of example. And for example, we have a set, and it has two elements, 2 and 4. So when we eliminate its element and or separate its elements in the form of 2 4 2 4, and these are, you see, 2 belongs to this collection. So that's why 2 is the subset of this set. 4 belongs to this collection, and that's why 4 is the subset of this set. This is our main set or father set, and these are their subsets. And 2 4, every subset has itself a subset, every set has itself a subset. And see other example 3, 5, 7. So empty set is always a subset of other sets. So every set, empty set, you can include empty set as a default. And 3, 5, 7. First of all, how to write the subset of a set? First of all, write one element separate in a set bracket, and for example 3, 5, 7, then pair wise 3, 5, then 3, 7, and 5, 7, then write all these three elements. Now here the question is that how we know this set has how many subsets. And for this we have a, for example, this set is consist of 3 elements, and it has 1, 2, 3, 4, 5, 6, 7, 8. It has 8 subsets. Then how we decide that if the element, if the set contains 8 elements, and how many subset it has? So that's why we have a formula for this. The number of possible subsets of a set is known by the formula 2 raised to power n, and where n is the number of the elements in a set. 2 raised to power n is our main formula from which we decide how many subsets of a set has. So for example, here n is 3. So 2 raised to power 3, and you know 2 raised to power 3 is 2 multiplied by 2 multiplied by 2. 2 2s are 4 and 4 2s are 8. For example, here this is our formula, and 2 raised to power, let's write me clearly, 2 raised to power 3. Okay, 3 these elements. So 2 raised to power 3 means 2 multiply by 2 multiply by 2. The 2 2s are 4, 4 2s are 8. So this set exactly has 8 subsets. Similarly, if the set have 4 elements, then it has 2 raised to power 4 elements. Calculate this, and you know exactly the subset of a set. So we see here, we see a formula, and next, so we move next. So next we see some examples by this formula. Of this formula, possible numbers of subsets are these. A has 4 elements, 3, 4, 5, 6. So these here 2 raised to power 4 and 2 raised to power 4 is equal to 16. So this set has 16 elements in its subset as a subset. So it has 16 subsets. Proper and improper subsets. When we talk about subsets of a set, then we have 2 main definitions: proper subsets and improper subsets. If A and B are 2 sets, here write capital B. A and B are 2 sets, and every element of A is also an element of a set. But at least one element of a set B is not an element of set A. Then A is called a proper subset. For example, 1, 2, 3, and it has element 1, 1, 2, and each element, this include in this set, but at least one element left. For example, here 1 include 2 and 3 left. So this is the proper subset. And here 1, 3 and does not belong to 2. So this is also, and there is no proper subset of empty set, and here empty set has no proper subset. So improper subsets, if A and B are 2 sets and set A is subset of B and set B is a proper subset of B, then it is improper. For example, this. So 1, 2, 3 belongs to this one. This 1, 2, 3 belongs to this. Then they have equal number of elements and no element left of A in B. So that's why B is the improper subset of A. So next, move forward. Power set. So next we see definition of a power set, and a set consisting of all possible subsets of given set A is called power set of A and denoted by P of A. Means we collect all possible subsets and collect them and write them in a bracket. Then it is called the power set. For example, AB has 2 raised to power 2 mean 4 elements in a subset. Then AB, we write the subsets of AB and then put them in a bracket, then it is a power set. Now see some important remark. If a set contains n elements, then the number of all its subset is 2 raised to power n, and we studied already 2 raised to power n. For example, x is equal to 1, 2, 3, then it has 3 elements and 3 subsets and 8 subsets and 2 raised to power 3 by the formula. And so the power set include write all these collection in a bracket and it is a power set. So now see some examples or some questions so that we make an idea how much we understand our previous topics. So write all the possible set of the following. Possible subsets, here we say subset, here is the writing mistake. So this is our empty set, and we know empty set has no subset. That's why it has no subset. Empty set is empty. No proper subset. Empty subset. Subset of empty set is empty, and one has 2 subsets, empty set and 1. A, B. Write them, practice them, and tell. Write all the proper subsets of the set. Here we have to write just proper subsets and write the part sets of the following. Write the part sets. How we write part sets? First of all, write all the subsets of the set, that set, then combine them in a collection of all these subsets. Then we have the resulting set is a part set. So practice these questions for your conceptual point of view. Now we see union and intersection. What is union and intersection? You see, we move forward slowly to the higher topics of group theory and higher topics. First of all, basically, we see what is set. Then we see definitions of its subset and proper and improper, and give some examples. And now we reach at union and intersection. If A and B are 2 sets, then the set consisting both elements of A and B is called union of A. For example, we have 2 sets, A and B, and we have make a one set which contain all the elements of A and all the elements of B. Then this resulting set is our union of 2 elements. For example, we have A 1, 2, 3 and B 2, 3, 4. And we write these. One belongs to 1, 2, 3, 2, 3, 4. You know, repetance is not allowed. So repeat. So avoid to repeat. For example, here we include 2. Then next time we do not write 2, 3, 4. So 1, 2, 3, 4 contains all the elements of set A, all the elements of set B. That's why this is the union of A, B. What is intersection? Intersection is the opposite of union, and if A and B are 2 sets, then the set consisting common elements of A and B mean those elements of A and B which belong to A and which belong to A, B. Here the word or, and here 2 words are important, or and. So in union, all the elements of A and all the elements of B. But here intersection, not A, or common elements of A, you write all the elements, common elements of A or and B. So here the word we do not write or. Here and word is most important. So we write common elements of A and B. And here is all the elements, both elements and all the elements, and here is common elements. So A and B. It is denoted by, and the sample of intersection is this, and the sample of union is this. Union sample is capital U and intersection sample is this. So if we write intersection of A and B, then we write this A intersection B, and this is over A, this is over B, and A intersection B means 2. First of all, A this, B this. So you know, 1 does not belong to B, 2 does not belong to B, 3 does not belong to B, 4. No, A and B have no common elements. That why its intersection is empty set. You know, empty set is the set which have no element. And in this example, 1 does not belong to this, 2. A and B have two elements which common it 2 and this. So here the A and here intersection of A and B is 2. Okay, that's clear. Or now we move forward. So we see union and intersection, and next we see commutative and associative laws. Commutative and associative laws of union. First of all, I want to start from basic. In your basic level classes, you know 2 plus 3 is equal to 3 plus 2, and this is answer is 5, and here is answer is 5. So changing the position of the numbers in addition does not have effect, and it has the same answer, and this law is called the commutative law of addition. Similarly, this law apply in our union, because as addition is operation in our question, similarly union is also a operation on set. So A union B is equal to B union A. For example, you write first A then B, and take union of A and B, then its answer is same as the union of B union A in this example. So A union B is equal to B union A. Similarly, this commutative law hold in intersection. So addition, multiplication, union, and intersection, these 4 operations hold commutative law. And here you clearly understand what is commutative law. Commutative law, changing position of 2 sets or 2 elements and then apply the operation does not make an effect, and our answer remains same, then this is the commutative law. So next we see next law. So commutative law of intersection. Here the one example of intersection A and B, and a intersection of A and B is equal to 1, 2. 1 does not belong to other set, so 1 we does not write 1 in A intersection B. So 2, the common elements of A and B are 2, 3, 4. So in its intersection is 2, 3, 4. B intersection A. B intersection A, the answer of B intersection is also 2, 3, 4. So changing the position of A and B, here we write A intersection B, here we write B intersection A. Changing the position does not have effect on our answers. So this is the commutative law of intersection. Our left hand side is equal to our right hand side. So now we see associative laws. Associative laws consist of 3 elements. In your basic primary level, you see we have example of numbers 2 plus 3 plus 5. So it is upon to you calculate, add first 3 plus 5, then add 2, then 3 plus 5, 8 and 2 10, and add first 2 plus 3, or then add 5. So 2 plus 3 5, and 5 plus 5 10. So they have equal answers. Okay, so this is the associative law of addition. Similarly, we have associative law of intersection. Similarly, we have associative law of intersection. Intersect, first know the intersection of two sets, then include third set. And here first take intersection of A and B and then include C. Then their answer of left hand side and right hand side remains same. Similarly, we have intersection associative law of union, and this is the definition of distributive law. In distributive law, first of A, B intersection C, then union, or first A union B, A union C, and then intersection. The answer is same. So these are our two distributive laws. This is the distributive law of union, this is the distributive law of intersection, and this is the associative law of intersection, and this is the associative law of union. So next we see our next definition. So relation. Now here we start very important topic of group theory, and it is relation. For the sake of better understanding of relation, we first of all we study about set, because all the definition of higher definitions of group theory depends upon set. And so first of all we see what is relation. And we have two A and B two sets, and you know what is set. We clearly define about sets. We have two sets A and B, and their Cartesian product of A cross B. Now I use the word Cartesian product, and here you confuse about Cartesian product. What is Cartesian product? So first of all we see Cartesian product, definition of Cartesian product, then we move forward to relation, because the definition of relation depends upon Cartesian product. So first of all AB, we have a pair AB, and the first element of this pair belongs to set A, and second element of this pair belongs to set B. Then if we write all the elements of A and B in such type of notation, then it is Cartesian product. So see one example. We have the set A and set B. A set 1, 2, 3, and B set 3 and 4. So now we have to write Cartesian product of A and B, and when we write Cartesian product of A and B, then we show this sample A cross B. So next we see next we see Cartesian product. Here one pair, make pairs 1, 3, then this 1, 4, then this 2, 3, 2, 4, 3, 3, 3, 4. Then now we wrote all the elements of A and B in pairwise according to this definition. Here the word for all is very important. All the elements of set A and all the elements of set B write in this form, then this collection is called Cartesian product. So this Cartesian product is very important in group theory. So we see definition of relation. Then every subset of subset is a relation from A to B. Then every subset of a Cartesian product. We defined Cartesian product in our previous slides, and now we say every subset of that Cartesian product is a relation from A to B. Let's see some examples. Our previous Cartesian product 2, 3 and 3, 3 is a type of relation from A to B. For example, in our previous group Cartesian product example, we choose one subset and one relation. For example, 2, 3 and 3. This is a relation. 2, 3 makes relation. 3, 3 makes a relation from A to B. Now we see some important marks. How we know the set? Similarly, this question is very have very resemblance to our subset. Then over the where we know how many set have subsets. Then here we know how many number of sets, number of elements in a Cartesian product. So we know by this formula, if we have a set A and it has exactly m elements, and set B and it has exactly n elements, and this is also called order of A. For example, we have order of A is equal to M. What is order? Number of elements in set A is order of A, and or we say it's cardinality of A. And A exactly have M elements, B exactly have N elements, and A and B. So how we know Cartesian product of A and B, how many elements, contain how many elements? Then A cross B have exactly M n elements. Number of elements in A cross B mean Cartesian product of A, B, or we say it's cardinality of A and B. Cardinality of A and B. So see some example. 2 raised to power mn is the number of relations that can be defined on Cartesian product. How many relations we defined on a set? So 2 raised to power mn, this is our main formula that defines how many relations that are defined on A cross B, or the Cartesian product of A and B. So now we see some examples of relations, and for example, we have set A and B. Then we have A and B, we write Cartesian product. The first step for relation is Cartesian product. So write the Cartesian product according to its definition. For example, A1, A2, B1, B2. So here M, number of elements in first set A is equal to M, and here M is 2. And number of elements in second set is N, and N is 2. So cardinality of Cartesian product or A, B is equal to M, N, and is equal to 2 2s are 4. So it Cartesian product of A and B has exactly 4 elements, and you verify it from here. A cross B has 4 elements, 1, 2, 3, and 4. So this is our cardinality. So possible relations are following. Possible relation, we choose one subset, this, so it has one relation. We choose this subset B1 from this set or from this collection. So this is a relation. On relation from where to where? Relation from A to B. So A2, here we have A2 and B2. These are the possible relations. Now we discuss about important definition of group theory, and it is function. Function is very important in the point of group theory in calculus and all higher level of mathematics. So it is very important to understand function clearly. So first of all, make a sketch what we study. First of all, we see Cartesian product. Okay, from Cartesian product we choose some subset and make a relation. Okay, from relation we choose some special type of relation and name it function. So first of all, we have set, define Cartesian product on it, and Cartesian product on it, then defined relation on it, and relation to. Now we move forward function. So these steps you have to sketch these steps in your mind when you study about functions. So a relation, first of all, we see what is a function, and a relation from A to B is called a function. Such type of relation which satisfy this condition. The condition is what? The condition is if each element of A, here is word each is very important, and I clear this word each in our next slide. Each is A belongs to A, and the first element appears exact ones, mean we have to write subset of the Cartesian product, but such type of subset which satisfy this condition, mean each element of A belongs to A, and the first element appear exact ones. So we understand the definition of function with the help of example. So see what is function. Here we have two sets A and B. Make Cartesian product of A and B. Now we write subset of that Cartesian product, and here I write two subsets of that Cartesian product. Subset, we can write any subcollection of that set is a subset. So 1, A, 2, B, 3, B, and this. Now here I have to decide which collection is which collection is a function, or which collection or relation is not a function. So this is the relation, but it is you see, uh, we have two conditions, or we have two main conditions for function. First condition is all the elements of A, each element of A, all the elements of A used in this subs in this. So you see 1, 2, 3, all the elements used in of A used in this sub collection, okay, in this subset. First condition satisfied. Then each first element of A appear once mean if we write 1 here, then we have not write 1 in any other pair. So 1, 2, 3. Here no element is repeat, so that's why we have each element of A distinct element and also distinct element. Both conditions of a function satisfy. That is why our first subset of this Cartesian product is a function. But here you see 1 and 1. Second condition is not hold here, because we write 1 2 times, and in our condition of a function we say the first element of a set appear exact once, but here 1 repeat 2 times. That's why we say it is not a function. So our first definition, according to our definition, our first example is a function and second example is not a function, but they both have relations, but they not one of them is a function because it satisfy the condition of a function, and other is not a function because it does not satisfy the condition of a function. Next we move forward. Our we see with the help of a diagram. For example, 1 is map on A, 2 is map on B, and 3 is map on D. All the elements of set A, B uh, repeat use, and no elements have mean A or B. All the elements mapped exactly once. So that's why this is the physical or graphical view of a function, or this is a graphical view of our second example here. 1 is map on A, 1 is map on B, mean first element appears twice. So that's why it is not a function, because in our function we have clearly two conditions. All these, this is our first set, okay, this is our second set, and we have to write all the elements of the set exactly once. Map all these elements of the other set, one set on another set exactly once, and or use all the elements. So one condition is hold here, all these elements of set A used or mapped on set B, but repeat here 1 is mapped 2 times. 1 is map on A, 1 is map on B. That's why it is not a function. So next function has two many types. For example, one function, onto function, and other many types. Now we see definition of a one function or injective function. Mean what is one function or injective function? So a function is said to be one if different elements having different images. For example, next previously see, this is our domain, and this is our range, and our range have image. And in one example, first example, you see 2 and 3 map on B. So 2 and 3 have same image, but in one function we have restricted in one another condition, that second in function we does not bound, we do not bound for the second elements of the pair of function. But here we have to note about second element, because different images, second elements is also unique here. So this is our cell, different elements having different images. So next see, for example, A and B, we have two elements in belongs to A, and if A does not equal to B, then f of A image of A. This is the notation of image of A, and this is the notation of image of B. Here I use two words, domain, two more different words as usual, two words, domain and range, and two words, images and mapping. So these four definitions I explain next, so don't be confused. So what we see, one, two, this is not a one function. To learn something in some definition, or to learn some new concept, it is necessary to learn about its counter example. Counter example, the examples which does not satisfy our definition and does not hold our conditions. So this is not a one function. Why we say this is not a one function? Because you see here, 1, 2, 3, 2, it is not a function. And the function which is first of all, for one function, we have a function, and it is does not satisfy the definition of one function. So it is not a function. When it is not a function, that is definitely not a one function, because for one function, a relation first have to satisfy all the conditions of a function. Now notes one thing more here. Here is A and A. We repeat second element twice, but in one uh, with the repeat of first element, we note either second element is repeat or not. If the second element does not repeat, then this is a one function. So this is the one function, because 2 is repeated twice, so it's not a function. Then this, if it is not a function, then it is definitely not a one function. So see example of A and B. Here you see 1, 2, 3 and B, A, B, C, and here I make a function 1, 2, 3. First of all, see all the elements of set A use in this set, and all the elements of A happens or appears exactly once, so it is a function. So when we say it is a function, then we move forward to the one function. So one function, second element mean images. Here one, A is the image of 1, B is the image of 2, and 3 is the image of C is the image of 3. So here this, for from this we see no element of B appears twice. That's why it is a one function. And graphically we say, for example, we have two sets. First we name this is our one set, and we named it A. Here it has 1, 2, 3, and here it has A, B, C. And this is our A set, and this is our B set. You know, this is our A and this is our B set. So map according to this mapping. 1 is mapped on A, so I mapped 1 on A. 2 is mapped on B, so I mapped 2 on B. 3 is mapped on C, so I mapped 3 on C. Here you see all the elements of first set use, no element repeat, and here is also not repetance, because once A become the image of 1 in one function, once A is the image of 1, then it definitely not become the image of other numbers. So A is used, then B is also. Similarly, B, when B become the image of 2, then B definitely have not become the image of other elements. So this is the clear view of one function, and hope so you learn from it clearly. So see one more example, and here 1, 2, 3 and ABC. 1, 2, 3, and here A is repeat twice, and note one notation here. If here we see F and A is related to B, and you this is the mapping from A to B. This is the notation of a mapping from A to B, and here 1A, 2A, 3B. So first of all, see either it is a function or not. So you see all the elements of A appears, and exactly once, and that's why it is a function, but it is not a function. Here we write not a one function. It is the counter example of a one function. Why it is not a one function? Because in one function we have our second element of the pairs unique or distinct, and when we write A once, then we do not write A again. So that's why this is not a one function. Let's see graphically 1, 2, 3, A, B, C. Here according to that, this is the mapping. So according to that mapped, here 1A means 1 is mapped on A. So we mapped 1 on A. According to this, we mapped 1 on A. Then 2 is mapped on A. So we mapped 2 on A. Here 3 is mapped on B. We mapped 3 on B. You see, here A is the image of 1 as well as A is the image of 2. So this is against the condition of our 1 function. That's why it is not a 1 function. It is a function, but it is not a 1 function. Next, we learn important definition of onto function. 1 function and onto function. Now slowly we move forward to higher topics. So first of all, you have to practice these concepts. So onto function and onto function, we have some definition. We define onto function with the help of definition. We have a set A 1, 2, 3 and B A, B, and we take a Cartesian product of A and B, and our how we write our Cartesian product 1A 2B 1A 2B 2A 2B 3A and 3B. This is our Cartesian product of onto function. Next we write subset. Relation may be a function or not. Here before reading onto function, we have to know about relation, and we know difference between of domain, range and codomain. These are the three basics and important definitions of group theory, and without understanding them, we do not learn about higher topics of group theory. So learn these topics attentively. What is domain, range and codomain? So with the help of example, I want to explain. So we have a set A, and it has 3 elements 1, 2, 3, and a set B, and it has 5 elements A, B, C, D, E, and we have if A is mapped to E. Yeah, for this is our writing mistake. So this arrow will be written here. So this is our function F, and mean we take some subset of Cartesian product of A and B, and this is 1, B, 2, C and 3E. And this here, what is the domain? Domain is the set of over all the first element of the function, because here this is our function and we have 1, 2, 3. These are the first element of the function pairs. So 1, 2, 3. This is a set of our domain, and we write it a domain of F. And what is range? Range is the set of all those elements which are the images of our domain. For example, B, C, E. Here you note one thing. Not all the elements of B become range. Range may be B, but not must in every case it is equal to B. So range is B, C and E. So codomain is A, B, C, D, E. Now you make difference between these three terms: domain, range, and codomain. In domain, we have to write all the elements of first elements of these functions. In range, the images in which domain elements mapped or images of domain is the range. And codomain is the set in which possibility of images ranges or images have. Mean codomain is the our second element or second elements of codomain. In codomain we have to write all the elements of our second set. So here is B is the codomain, or now A is domain, B is codomain, and range maybe in some cases it is equal to B, but not in all cases. So domain and range, we learn about domain and range in another point of view, and you see, you can understand domain and range with the help of examples. And it is as a input and output. For example, you give some input to computer, and computer gives you some after processing, computer give you some output. The input or information which you give to computer is your domain, or the computer which give you some answer is the range, and possibility of all the answers is our codomain. So we see one another example of domain, range, and codomain. And here is we have two sets A and B. We write some function containing A and B, and here we see domain and range and codomains of A, B, A and B. So here we have one set named A, and here we have our second set, and here from without you mapped, and see, one is mapped on A, two is mapped on B, 2 is mapped on B, 3 is mapped on C, and 3 is mapped on C. Here one is mistake. Here is 3 is mapped on C, not A. So 3 is mapped on C. Here is writing mistake. Correct it. 3 is mapped on B, so 3 is mapped on B. So these are our domain, or these are our these complete set is our codomain, and A and B, which become the images of these elements. Then these are our ranges, and in here we have two different sets, which are one in which one is range and one is codomain. So next we see learn more concepts. So we analyze what we analyzed from our previous example. The very first element appears exact once, and a relation. Now we see a relation which is a function, and a relation which is not a function, because learning about functions and relations is more important, in fact most important. So our previous Cartesian product it is a function because it satisfies the above conditions, and it is not a, this is the subset, and it is violates the condition 2. Condition 2, what is the condition 2 of a function? Condition 2 of a function is that we do not repeat first element here, and here we repeat A and B, so it is not a function. So we learn we see, as you know, we see about definition of onto functions. We start to learn about definition of onto function, and in onto function we see 4 terms: domain, range, codomain, and image. And then so that's why for us, before start of onto function, we learn about domain, range, codomain, and with the help of example and clearly understand about all these terms. Now we learn about onto function, and after learning the definition of domain, range, and codomain, we can learn about onto functions easily. So A and B, we have two sets A and B make a function. First of all, what is our first step? Make a function. Then decided whether it is onto function or not. In onto function, you see, first in function, definition of function, we have to use each element of A. And in onto function, now with the each element of A, we write each element of B. Mean all the elements of, in just simple function, it is not necessary to make the all the elements of B as the images, but here write all the elements of B as the images of all the elements of set A. Then it make onto functions. Here we have B and it has two elements, 3 and 4, and you have to write 3 and 4 all the elements, so it is onto function. So counter example which is not onto function, because you see here 3 and 4, you have two elements 3 and 4, but it's in the image, or in other words you say range. In onto function, range and codomains are equal. When ranges and codomains are equal, then it is onto function, otherwise it is not onto function. Here you see B contain two elements 3 and 4, but here the range is just only 3 and range is not equal to our codomain. That's why it is not an onto function. In onto function, we clearly have same codomain and range. That's why you can estimate about onto function seeing its domain and seeing its codomain and range. So here is our one another example. We have set of natural numbers, and in our very first minutes of this video, we learn about natural numbers and we see what is natural number. Natural number is the set that starts from 1 and so on, continue. And these three dots are ellipses, and we shows that this is set is continue as our counting. R is relation. Now we have to define relation. Relation mean we have to write such elements of A and B in pairs, and these A and B satisfy this condition. Mean A is equal to B minus 1. Mean B minus 1. A mean first element is less than 1 unit from second element. So here if we have 2, then here we have 1, 2 minus 1. Here we have 3 and we write 3 minus 1, 2, 4, and 4 minus 1, 3, and so on. So it is a function. It is not onto function. Why we say it is not onto function? You can see it is in onto function, our domain, codomain, and ranges are same. All the elements of natural numbers are used. But here you see 2 from our range starts from 2, 2, 3, 4, and it continues 5, 4, 6, and 7, 8, 9, and so on. But 1 is not used here. But we have codomain all the set of natural numbers. Why we say it has codomain all the set of natural numbers? You see here n cross n first, and it is mapped on n. So this is our domain, Cartesian product of n cross n, natural numbers ki Cartesian. And here we have natural numbers as a range. So but our range, our codomain does not equal to our range. That's why it is not onto function. And onto function also called surjective function. So other name of surjective function, don't be confused with new word or term. For example, we have two sets A and B, and A has three elements, 1, 2, 3, and B has 3 elements, A, B, and C. and here we see 1a, 2b, 3c is a 1 function. So if it is a 1 function, why you say it is a we say it is a 1 function? So see, what is 1 function? In 1 function, different elements having different images means images are also unique. So you see here images are unique. A, B, C are our images, and these are unique. So it is a 1 function. And all the images, all the elements of B are used, mean our range is equal to codomain. So it is also onto function. So this is our mapping: 1 map on A, 2 map on B, 3 map on C, and this is our 1 function. This is also onto function. So this is the one of very important example in which this is an example is our this example is our function. Then it became 1 function, then it is became onto function. So in general way, if one function need not to be a onto function, and onto function need not to be 1 function, but it is some particular type of example in which this function is a 1 and also onto. And this is the some points. I think we learn about these points already. So these in these points we here we make a sketch what we learn in these topics. You see, we learn from very basic, then slowly move toward our next topics and learn some more important terms. So first of all, we learn about set. What is set? Okay. Then we learn about types of set, counter examples of set. Then we learn subsets, about subsets. Okay. Then we learn about subsets. From subsets, we see two definitions: proper subset and improper subset. And we see some example of proper subset and some example of improper subset. And we see empty set is the particular type of set which has no proper subset. So from set subset we see some properties of sets, and in these properties we see properties of set, and in these properties we learn about commutative law and commutative, associative, and some basic definition operations on sets, means union, intersection, and all these. So from this we learn about after learning about union, intersection, we see some definition, we see some example and definition of a power set. And what is power set? You know, all the subsets of a, if we collect all the subsets of a set, then it is make power set. Then we learn about some important formula of a power set. And after learning about formula of a power set, we move forward to our higher topic, and it is a relation. So for relation we need Cartesian product. So for relation here, due to mouse we may have a difficulty for writing, but now try to write. For relation we have to make we have to learn about Cartesian product. And you know, Cartesian product is defined on two sets. Okay, and the sample of Cartesian product is this multiply. If we write this is the sample of Cartesian product. And then we know about number of elements in a Cartesian product. and then we study some examples of Cartesian product. Then we see very important definition of a group theory, and which is a function. So we see what is a function, and we give some one another example of function, in which we take example as a machine. For example, one, we give input some machine, after processing the machine give us output. Similarly, in that way we give some input and some domain to our function, this function process and give over some output as a range. So we see, we can see also this the definition of function from this point of view. Next we learn about function. After function we learn about one function. So when we learn about one function, we have three terms: domain, range, codomain, and images. So then we stop our after stop one function, we see basic definitions of domain, range, codomain, and all these terms, and then we move forward to our onto function. And in our onto function, so in our onto function we make examples, which is a function. But here you have to learn two basic things: any one function and onto function needs to be a function first. First of all, it became a function. First of all, when you determine the collection or set is a one function or onto, then you have to decide first either it is a function or not. If it is not a function, then it is definitely not a one function, and definitely not an onto function. So that's why for C11 and onto function, you definitely see either it is a function, because every relation is not a function. Okay, so this thing we explain here, because first you see, this is the example of our function. It is a function because it satisfies the condition of it. It is not a function, but it does not mean it is not a relation. Every function is not every relation is not a function, but every function definitely a relation, because we derive functions from relations. That's why one and onto functions, we have every one function needs not to be a onto, and every onto function needs not to be a one function. So this is our main difference. And in sometimes we have such type of functions which is one and also onto, and but this is our particular case and not happening in all and general case. So don't be confused with that, and use a general case. So you make a clear idea from these slides about this. Next we learn about more higher topics of group theory, and you have to make some practice of these topics, because without practice it is not possible to learn something. Practice makes some imperfect. So that's why you have to use these as examples. Okay, this is Cartesian product, and this is a relation which is not a function. And you see, first of all, I want to see something more important from here. For example, in our previous slides, you see one example, one important point about functions, and this is one thing, onto function. This is our onto function. So here a relation may be a function or not. So similarly, a relation may be a function or not. Similarly, one function may be onto function and not, maybe, or onto function, maybe not. So this is our main theme of our topic. So I want to tell you about counter examples. Counter examples have great importance when we study something about something new, because here we see a one counter example, and it is it shows how we learn, or how at what extent we learn the definition and also we study it. So from these definition, here I want to explain something. And now we study all the terms, and from this graphical view, you have to able to tell me what is domain, range, codomain, one function, onto function, function, and relation. So starts from, so first of all, it is a relation. Okay, every one thing map on another thing, then it makes a relation, but every relation is not a function. So you see, it satisfies two definition or two conditions of a function, so it is a function. Next we see either it is a one. So for one, these are needs to be distinct, so it is not a one, because in one a and b mapped only once. So but here b is the image of 2, b is the image of 3, so it is not a one function. Next, we see it is onto function. Our range and codomains are equal. Here we have domain is A and B, and range is also A and B. So our domain and codomain are equals. Now I write here. Here we have, this is our set A. You see, this is our set A. This is our set B. So here our range is A and B, because ranges are those elements which become the images of first set. So, and here we the set B, and B is also equal to 1 and 2. So that's why our range and codomains are equal. So this is onto function, and but it is not a one function. If it is a one function, then if we move this red line or this red mapping, and then it definitely become one as well as on to, and this is the relation of a function. Hope you understand it better.